Welcome to this lecture. This is the second lecture of week 3. In this week, we are discussing about convergences of sequences of random variables. We have already seen there are two types of convergences, one in terms of LP, another in terms of almost sure convergence. In the first lecture of this week, we have discussed the link between these two, and we have actually seen that neither one implies the other. In this lecture, we are going to talk about another new mode of convergence. So, let us move on to the slides. So, we are again continuing with the setting that we are having some measure space which is denoted by omega f mu or some probability space omega f p. So, all the measurable functions or random variables will be defined on any of these measure spaces or the corresponding probability spaces respectively. Now, we are interested in looking at another new mode of convergence involving either measurable functions or random variables. So, let us start with the definition. First, we give the definition in terms of measurable functions. So, this notion is called convergence in measure. Idea is this: we are given these functions f, f1, f2 and so on. All of these are defined on this same measure space, and we say that the sequence f n converges in measure to the function f if for all epsilon positive this size goes to 0 as n goes to infinity. So, let us take a minute and understand this definition. What we are looking at is the set involving all points in omega such that modulus of f n omega minus f of omega, that quantity exceeds epsilon. Now, once you look at this set clearly depends on n, and we are looking at the size of such sets. So, this quantity again depends on n. Now, what we are asking is that as n goes to infinity, does this quantity goes to 0, and if this happens for all possible epsilon positive, then we will say that the sequence f n converges in measure to the function f. So, this is the nature of closeness which we are trying to capture. Now, the similar definition can be restated for random variables, and we shall call this convergence in probability. Again, the idea is similar. We are having these random variables x, x1, x2 and so on. All of these are defined on the same probability space omega f p. Now, we say that this sequence of random variables x n converges in probability to the random variable capital X if for all epsilon positive these probabilities go to 0. Now, here we note that the event that we are interested in is the set of points in the domain such that modulus of x n omega minus x of omega exceeds epsilon, and what we want is that probability of such quantities should go to 0 as n goes to infinity. Now, again we are trying to capture a measure of closeness between x n and the limit random variable x. Now, to denote this notion of convergence, we will use this symbol, and on top of the arrow we will write this probability measure to denote that this is convergence in probability. Now, let us rephrase these conditions that we have stated for convergence in probability. Observe that if we choose any epsilon positive, then the event that x n minus x modulus value of that greater than epsilon, that is contained in the event that this quantity is greater or equal to epsilon. So, clearly this event is a subset of this event, and therefore, the inequality in terms of the probability follows. Again, if you start with the event that modulus of x n minus x greater or equals to epsilon, then that event is again contained in the event that modulus of x n minus x greater than epsilon over 2. And again, similar to the earlier property that we have discussed, that now the probability of this middle term is less or equals to probability of this right hand side, and hence we have this nice upper and lower bounds for events involving greater or equals to. Thus, equality symbol is included here. Now, if it so happens that x n converges to x, then both these left hand side term and the right hand side term as per our definition goes to 0, and hence as a consequence these probabilities go to 0. So, here we have now included the equality in the event, but on the other hand, if the probabilities involving these equalities they go to 0, then of course, the left hand side of this inequality that we have stated earlier will tell that also that the limit of the probabilities where only there is a strict inequality, that quantity also is going to 0, and therefore, this condition where the equality is included, that is equivalent to the convergence in probability. So, sometimes it is easier to think of events where the equality is included, and sometimes the equality will be excluded, and this will sometimes help in computations. So, this is a very simple observation that we performed, and this gave us a very simple alternative formulation of convergence in probability. But we are now going to see some other interesting reformulations of convergence in probability. So, here what we look at is the property that probability of any event, if we complement it, that is exactly given by 1 minus the probability of the original event. And now, using this fact, what we can conclude is that the convergence in probability for a sequence x n to a random variable x, that can be restated as these conditions, that the limit involving the probabilities where we are now looking at less or equal to rather than greater or equals to. Remember the event that mod x n minus x greater than epsilon, if you complement it, we will exactly get this opposite condition less or equal to epsilon. And for the original event, the probabilities of that goes to 0 if you have convergence in probability. Therefore, in limit they must have full probability. Therefore, the convergence in probability will imply this condition. But then again, if the limit of this less or equal to type events is 1, then just appealing to this property of probability of complements will again give us the fact that probability of the original events which is greater than epsilons, which involves greater than epsilon, they converge to 0, which gives us convergence in probability. Therefore, just by appealing to this standard observation which connects probabilities of events with their complements will give us this equivalent condition, and that limit must be 1. Now, again we can repeat the same argument by starting with greater or equals to type events, and we will end up with these complementary events, and their probabilities must go to 1 if you are talking about convergence in probability. And again, as discussed, these kind of conditions are also equivalent to convergence in probability. Now, again what we are looking at are convergence in probability, and so far we have used very elementary properties of probability to reformulate the definitions and restate these conditions in various equivalent formulations. Now, that we have some idea about this new mode of convergence, which is convergence in probability, it is now time to try to compare the earlier two modes with this new mode. But before we do that, one important comment is this, that all three modes of convergence that we have seen so far, namely convergence in LP, convergence almost surely and convergence in probability, all these three modes are defined only when the random variables are considered on the same probability space. This is the important background. Whenever we are going to look at any one of these three modes, you need to look at sequences of random variables, all of which must be defined on the same probability space. Now, before we start comparing, let us look at one specific example of convergence in probability. Recall that if you are working with a exponential random variable with some parameter lambda, which is some positive number. So, just to clarify, this lambda is not denoting the Lebesgue measure here, this is some real number which is positive. Now, if y is a exponential random variable with this parameter lambda, then we have this structural property in terms of the tail bounds or tail probability bounds. It is that probability that y greater than a given real number small x has this explicit expression that if x is less or equal to 0, then this probability must be 1, and if x is positive, then the tail bound is exactly this. And as you can expect, as x goes to plus infinity, then these tail bounds actually goes to 0. So, that is essentially what we expect. But for exponential random variables, we have these nice explicit expressions. Now, using this exponential random variables properties, we exhibit some example of convergence in probability. What we do is that we look at a sequence of random variables, all of which are defined now on same probability space, and with these interesting distributional properties that the nth random variable is defined with the distribution exponential with the parameter n. Now, if you take that, then for all epsilon positive, what we get is that the limit of these probabilities, where we are looking at mod of x n greater than epsilon, that quantity goes to 0. So, that is what we would like to show. So, here what we first see is that all these random variables are anyway taking non-negative values. So, therefore, this probability is same as the probability that the nth random variable takes the value greater than epsilon, and this is where we plug in the value of the tail bounds that we have observed earlier. Now, here as n goes to infinity, we immediately will conclude that these quantities are converging to 0. So, therefore, what we have concluded is that the random variables x n, nth random variable having exponential n distribution, will converge in probability to the constant random variable 0. All right. So, this gives us interesting example of convergence in probability. All right. So, with this explicit example at hand, we now start comparing the convergence in probability with the earlier two modes, namely convergence in LP and almost sure convergence. First, we have this interesting result which says that almost sure convergence implies convergence in probability. To see this, what we first do is that we recall one equivalent formulation of almost sure convergence. First, we observe that for any epsilon positive, probability of this event is less or equal to probability of the right hand side event. Why? Because the left hand side event that we are looking at here, that is contained in the right hand side event, and therefore, the probabilities must follow this monotonicity relation that the left hand side probability is less or equal to the right hand side probability. Now, using this observation, and if we are already given that x n's converge to x almost surely, then we immediately have that the probability on this right hand side events, they converge to 0 as n goes to infinity, and this happens for all epsilon positive. This was discussed earlier in remark 1. Please go back and check. Now, given that we have almost sure convergence and probabilities of these events are going to 0, we immediately conclude that probability that modulus of x n minus x exceeding epsilon, those are also going to 0 as n goes to infinity, and hence what we have is that x n's must converge in probability to the random variable x, which is what we wanted to show. So, therefore, what we have is that almost sure convergence implies convergence in probability, and therefore, almost sure convergence is a stronger notion of convergence of random variables. Now, let us look at some interesting comments based on the type of proof that we have made. We have earlier remarked that convergence in almost sure convergence sense can be reformulated in terms of certain Cauchy properties. We do the same for convergence in probability. We can actually show that x n converges to x in probability if and only if for all epsilon positive, the probability that the fluctuation involving the nth term and the mth term can be captured by this epsilon through this probability is going to 0. So, if n and m goes to 0, x n and x m, the difference of that exceeds epsilon, that probability must go to 0, all right. So, that is equivalent to convergence in probability. We had discussed about a similar property for almost sure convergence in remark 1 part 3. Now, this last condition that we ended up with, we will refer to this as the sequence being Cauchy in probability. This is easily understood that we are looking at n and m simultaneously going to infinity, then the nth and the mth random variables are close together, but in terms of these probabilities which we are capturing through convergence in probability. So, this new condition which is Cauchyness in probability is linked to convergence in probability. We will discuss about this Cauchy properties through convergence in probability later lectures. All right. So, it is now time to compare LP convergences with the convergence in probability. Note that we are working with any number p between 1 and infinity, both 1 and infinity are included in our discussion. First, for the simplicity of the argument, we will consider the case p between 1 and infinity, infinity excluded, 1 included. In this case, what we would like to show is that LP convergence implies convergence in probability. So, let us see this. If we are already having the convergence in LP, then these expectations which involves the pth absolute moment of x n minus x, that goes to 0 as n goes to infinity, that is given to us as long as x n's converge to x in LP. But we go back to this following variant of Markov's inequality that was discussed in week 1 theorem 3. Recall that for any random variable y, the probability that mod of y exceeds epsilon can be dominated by this quantity involving the pth absolute moment of y factored by epsilon to the minus p. So, this is the upper bound of these probabilities, and this is true for any random variable y, and this holds for any epsilon positive. Now, using this, what we do is that we apply this inequality to x n minus x, that random variable. Now, note that probabilities of these events that can now be dominated by epsilon to the minus p and the pth absolute moment of x n minus x. And since x n converges to x in LP, these quantities go to 0 as n goes to infinity, and therefore, probabilities of these events which we consider for convergence in probability, they go to 0. Thereby, we ended up showing the sequence x n converges in probability to the random variable x. Now, here what we have shown in the first case is that for p finite p, the LP convergence implies convergence in probability. Let us look at the remaining case where we consider the situation that p is equal to infinity. Now, if x n converges to x in L infinity, then in our earlier discussion from week 1 note 18, we have that convergence in LP for finite p follows, all right. So, first we are going back to this discussion in week 1 that L infinity structures are stronger than LP structures where p is finite. So, when we are working with infinity convergence, then whenever we are considering p between 1 and infinity, we will also get the corresponding convergence. But then for such P, we already have established the fact that LP convergences implies in probability convergences. So, therefore, we first go from L infinity convergences to LP convergences and then go to in probability convergences. Therefore, combining all these observations, we conclude that L infinity convergence implies in probability convergence. Now, combining the two cases that we have considered, in the first case we have taken P between 1 and infinity, infinity excluded. In the second case we have taken the case of L infinity. So, both these cases we have separately shown that convergence in probability holds. Taken together, we conclude that LP convergences, no matter what value of P we consider in this range, we must have convergence in probability. So, therefore, convergence in probability is a weaker notion of convergence than convergence in LP. Stated other way, convergence in LP is a stronger form of convergence than convergence in probability. Now, we would like to talk about the other direction of these implications, meaning can we see whether convergence in probability implies either of the almost sure convergence or convergence in LP. So, what we show by examples that neither of these converge statements hold true in general, all right. So, we go back to the examples that we have considered in our first lecture of this week. So, just to recall, in example 2, we had actually constructed a triangular array of random variables with this property that the triangular array of these random variables converge to 0 in LP, where P is chosen in this range. But this sequence had this property that it did not converge almost surely to anything. So, we have shown that it cannot converge almost surely. So, we had one example which had LP convergences, but not almost sure convergences. Now, in this example, if we look at further, then from our discussion that we are having now, in these propositions that we have proved so far, will tell us that LP convergences that is true in this case will give us also in probability convergences. Therefore, this triangular array of random variables that we are considering now converge in probability to 0. This is simply using the fact that LP convergences imply in probability convergences. But now, in this example we do not have almost sure convergence. So, therefore, this example shows that even though the in probability convergence hold, the almost sure convergence need not hold. So, the converse to proposition 2 earlier may not be true in general. So, we show by another example that in probability convergence holds, but LP convergences does not hold. So, that will give us the converse statement to proposition 3 is not true in general. So, let us see. So, to do this we again revisit one example that we have seen in our previous lecture. So, there we had discussed, we had explicitly looked at this sequence of random variables such that they do not converge in LP, but they converge almost surely to 0. Now, by our earlier proposition, since almost sure convergences imply in probability convergences, we must have that this sequence of random variables converge in probability to 0. But here we do not have the LP convergence, and therefore, what we conclude that our earlier proposition 3, the converse of that is not true in general, that is convergence in probability may not imply convergence in LP. So, therefore, the three modes of convergence that we have seen so far are connected in this way, that convergence in LP implies convergence in probability. Again, almost sure convergence implies convergence in probability, but none of the opposite directional statements are true in general. Okay. So, if you try to go in the opposite directions in general, they need not be true. So, what we typically have are additional sufficient conditions through which we might be able to obtain these other type of convergences, starting with convergence in probability. We shall see further discussions of these in the following lectures, but before that recall that the first two convergences that we have seen, namely convergence in LP and almost sure convergence, again neither of them imply the other, but we are again going to see some further conditions which helps us connect these two convergences. For example, we had already discussed earlier the variant of DCT, meaning with certain appropriate integrability conditions, almost sure convergences actually imply LP convergences, but again with some additional integrability assumptions. So, we are going to see results of that type which will help us further understand the link between these three modes of convergence, and this is quite important to our discussions that we will do in the later half of the course. So, the consolidated formulation is that the three modes of convergence, LP convergence, almost sure convergence and in probability convergence, have certain links, in the sense that convergence in probability is the weakest notion of convergence, which is implied by the other two, but none of the other directional statements are true in general. We stop here. Thank you.